Hello everyone, my name is Charles Heatherly. I am a senior in the Ocean Engineering program here at USM, and today I'm going to be presenting my senior project on titled Harnessing Random Linear Motion and Educational Wave Energy Conversion System. So to give you guys a little bit of background and my motivations about this topic in general, ocean waves can generate between 20 to over 80 kilowatts per meter of coastline. That's the amount of potential energy that exists in those locations. And that is visually represented here on this graph, where you can see the organization or clustering of all of the potential wave energy all over the world. And then below it, you can see more specific locations that might be more familiar and their corresponding wave energy densities. So essentially, 1 meter of on the lower scale, 20 kilowatt per meter coastline could power up to about 16 homes. And that's just only 3 feet. So that's an enormous amount of potential there. If someone were to take advantage of a much larger piece of coastline, you could power entire cities with this technology. And the good thing about wave energy is it's pretty consistent. It's always there. Some locations don't really have much activity, but the places that do are pretty consistent with that. So I wanted to develop a small-scale, interactive, hands-on system to help engineering students learn about these things by putting their hands on something physical, allowing you to connect the theory and all the math to something in front of your face. And one big motivation why I think this is important is because in the next 100 years, our traditional energy methods are going to begin dwindling and running out, like fossil fuels and stuff like that. So renewable energy is something that's really important that is understood within the engineering community so that we can start working towards a more reliable energy future. So a little bit of background on wave energy conversion itself. There's lots of different devices that harness wave energy currently. Here we have a couple different mainstream methods that are used. There are fixed surge converters, which is here. These guys are fixed to a wall or a breakwater or something like that, and they move up and down with the wave motion. Then you have floating surge converters here that go up and down with the waves. And then you have surface attenuation devices like this, which is what I took my inspiration from, more specifically the Balamis wave energy converter. So my objectives for this project were to develop a small-scale wave energy conversion system tailored specifically for educational use so that it could visually demonstrate the conversion of wave motion into electrical energy. To do that, I wanted to design a dual-piston hydraulic system to convert the linear motion into steady rotational motion. To generate my electricity, I wanted to integrate a hydroelectric turbine, and then all of this is for the educational aspect. So I wanted to promote awareness of renewable ocean energy through a hands-on demonstration. And then also I wanted to strengthen my skills in fluid mechanics, hydraulic system design, as well as CAD modeling and prototyping. So to show you a little bit of how my system works, we have my hydraulics diagram here. So buoyancy causes the float to move up and down. The float is connected to 2 pistons in a layout just like this. As the float rises, it pushes the top piston in and decompresses the bottom, and vice versa when the float falls. And you can follow the green path on either diagram. In the state that it's in the picture, the flow will follow the green path. So essentially, in this state, the flow will leave the piston going to a high pressure reservoir, and then from that high pressure reservoir it flows through the turbine into the low pressure reservoir, and then the decompressed piston pulls fluid from that reservoir. I have check valves, which you can see there's 4 of them, got those blown up for you so you can see them more closely and understand how or what direction they allow flow in. And the check valves allows me to maintain unidirectional flow through the turbine so it doesn't spin it backwards. So a huge part of my project was the mechanical design of my system. So you can see that here. I wanted to go with something clear so that you can see all the internal working parts and be able to learn from it just by seeing it. Essentially, I have an exploded view of the model here where you can see all the different components. I have custom end caps at 0.1. We have the custom pistons at 0.2. Custom pressure reservoirs at 3. And then we have the cage and the housing 4 and 5. So the cool thing about the cage is it's entirely 3D printed, and I made it in such a way that it holds all of the components together, and you can actually take the housing off while still having all the components be in there where they're supposed to be. So you can get closer with it, observe it better, do any maintenance that's necessary, and because it's 3D printed, if something breaks, you can always print a new one. Another key component here is the restrictive hinges. So that's bullet 6. So the reason why I have restrictive hinges is so that my pistons can only travel a set distance so that I don't damage the actual hydraulic cylinder of the piston itself. So talking about system motion, so when this system would theoretically interact with a wave crest, as you can see in the top picture there, it would rise. Excuse me. You can see the arrows there, and should remind you of the system diagram we just looked at, because that's what it is. But when the float rises, it pushes the top piston forward and pulls the bottom piston back, vice versa for when it experiences a trough here. And then after a few oscillations, the high pressure reservoir will become pressurized thanks to the compressible element within the reservoir. And then it will begin allowing a smooth, continuous flow through the turbine, generating electricity and then illuminating an LED. So for fabrication and testing, I had my custom parts CNC machined, which includes my custom pistons, pressure reservoirs, and custom end caps. You can see the pressure reservoirs here, the custom piston assembly, and then the end caps are here, 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 and there. But as far as testing goes, and I 3D printed the whole cage and the hinges. But as far as testing goes, that was just me physically testing in a quote-unquote simulated wave motion. Just kept a reasonably steady pace, moving the float up and down, and inspected for leaks and essentially system success to see if it would spin the turbine. It did. Some challenges that I overcame within this whole process was the housing came in with a smaller than I expected internal diameter, and so did the hydraulic cylinder for the pistons. So I had to make alterations to all of my components so that they would accommodate that new internal diameter. And I had to use a Dremel to increase the diameter on the inside for the housing so that it would fit my custom end caps, because I had those machined and I couldn't essentially reorder them because that was not accounted for in the budget. And then for the pistons, I took my custom piston heads, which are these guys here, and just sanded them down until they fit inside of the tube. So, overview of my budget. The main things, the most expensive things in my system would be the housing, custom machine parts, hydroelectric turbine, hardware, tubing, adhesives, and then miscellaneous stuff. Those were the most important parts of my system. Overall, it cost about $1,130.52. that was made possible through the DCUR funding with the Eaglesburg grant. I was given $1,000 for that, and then the OE fund, which was is sponsored by Systems Integrated Government Services Division, covered the rest of that. So constraints that I had in my time doing this project was system size and complexity had to be minimized to control costs. My custom parts had to be outsourced to overseas vendors, which took or increased the time of it being delivered. And that was due to whenever I was searching for vendors to do this, most of them in the United States were wildly expensive. Time constraints, being that this is a fixed semester timeline, there was no real flexibility there. So I had to limit my testing as well as the redesign cycles of the prototype. And then I was also constrained against using advanced features like real-time power monitoring. It's something that I wanted to do, but it's gonna have to just be something that I do in the future. And then instead of having my my structural cage and other parts machined into or using something more durable, I had to 3D print them, which was fine for this prototype, but in the future it would be cool to have something a little more durable. And then I had to do modifications to my design due to the inaccurate off-the-shelf material dimensions. Broader impact of my project kind of falls into 3 categories. The first one is the impact on the environment. My project promotes sustainable energy awareness through wave energy education, as well as encouraging the exploration of renewable alternatives to fossil fuels. It provides a tangible visual tool for teaching ocean energy concepts. It also enhances the understanding of hydraulics, fluid mechanics, and energy conversion in the classroom. Societal impact, it hopefully will inspire future engineers to innovate in marine renewable technologies, as well as supporting broader efforts to transition towards sustainable energy systems. So, being that I had all those things, it met my objectives that I originally set for myself. And then for the takeaways and lessons learned on my part, I gained some technical skills in fluid mechanics. I was able to apply real-world hydraulic systems design. I was able to learn more about CAD modeling and prototyping through my custom parts design and system integration. And then my hydraulic circuit design, I learned about managing pressure, flow control, as well as component interaction. I also got some professional skills from this, which is project management. A huge thing is balancing your budget and timeline, as well as your sourcing constraints. Those things put a very large slowdown on my process. So they're really good skills that I have gotten out of this. Technical documentation, being able to take your engineering explanations of things and make them more understandable to someone that is unfamiliar with your project is very important. And that's something that I was able to learn through this project, as we had to essentially report on our progress every single week. And then problem solving is another professional skill that I developed further throughout this project. I was able to adapt to unexpected complexities throughout the development of the project. And then unexpected lessons. It happened to be in my case that it was easier for me to just design custom components for my system whenever I couldn't find them commercially. And that's mostly just due to time, but that's not the case for everything. And then vendor and material variability required flexibility and quick redesigns on my part. Like I said, some stuff came in with dimensions that I was not expecting. And then another unexpected lesson is that carbon fiber infused filament is very damaging to 3D printer nozzles. After just a few prints, it had essentially destroyed the whole nozzle on the 3D That's good to know. For future work, I really want to look into advancing my project in a way that you can input wave parameters into a device and then have those parameters be shown through the demonstrator, and then you can do different experiments, labs, and stuff like that on wave energy conversion, and you can learn how, depending on the different wave parameters, the difference of how the system reacts. And then I also want to explore alternative energy storage. So either having small batteries in there that can be charged through its actuation, and then I want to refine the fluid circuit design to be more efficient and for a smoother operation. Oh, and I also want to integrate a digital display for real-time voltage and power output monitoring, so you can actually visually see with the movement of the system, you can see the amount of power that's being generated. I would also like to fully waterproof the system so that it can technically be tested in a waveflow environment. Conclusions and acknowledgements. So through this project, I designed, built, and tested a small-scale wave energy conversion system. I demonstrated the energy transfer from simulated wave motion to LED illumination, and that it provides a transparent, hands-on educational tool for renewable energy learning, as well as reinforcing the core engineering principles like fluid mechanics, hydraulics, and energy systems. And I wanted to give a special thanks to the DCUR for funding this project, as well as to Dr. Deuce for his guidance and support. And then I wanted to express some gratitude to the Undergraduate Symposium on Research and Creative Activity for the opportunity to present my work, and I am honored to receive the Donald Draco Prize for Excellence in the Environmental Analysis of Devices category at the 2025 UGS competition. Thank you. Does anybody have questions?
What was the thought process behind using a liquid like water instead of pneumatics or an alternative?
So that's a great question, definitely one that I've contemplated myself. So originally, I started the thought process behind the whole project after finding the turbine. I kind of designed the entire thing around the turbine because there's very limited available components that would just generate electricity by spinning that I could fit into a small system like this. And essentially it was made for water. The reason why I want to do that is because I didn't want to have to design and make the energy converter itself. I just wanted something I could buy off the shelf. And from what I found that was the best one that I found that I liked. And that would require the use of water, so that was that. I did think about using a different fluid, which was a super low viscosity silicone-based fluid, and I was hoping to, with the use of that, to reduce the amount of force necessary to push the fluid through the system. However, that came back with issues of it was super, super expensive. And also I was worried about the compressibility of the fluid, and I was worried that it was going to have some kind of springy reaction through the system. And so I just wanted water.
Did you ever look into using a more mechanical approach instead of water or air?
I did. Last semester I looked into a purely mechanical approach, as well as to a few other ones that I don't actually remember anymore. But I looked into just different stuff like that, but I wanted to go more with the style that's used in the field, and I think that you can learn a lot more from seeing that versus seeing something that's purely mechanical.
So your initial inspiration was the Palmer system? However, it seems like you ended up with a system more like the wall-mounted system, right?
The what?
The wall-mounted system, if you go to your...
Yes. The way that this technically works right now is the mechanical side of it with all the main
Go to the
components.
slide. Yeah, go all the way to the where you show all the different systems. Yeah, this one here, right? So you pretty much have a fixed search.
Yeah, so
Converter
that's how
automatically.
it technically would have to work right now. Ideally, I would want to actually do the calculations to figure out the wave parameters that this would work most efficiently at, and then I would also like to figure out a way to actually have this be balanced. But right now, it's definitely not. It would just probably tip over if it was actually in the water or sink. But the goal was to have it be more like a surface attenuator. That's the style of it, at least. But the functionality right now of the prototype is definitely a lot closer to this guy.
You remember our discussion in OE 210 about the
Maybe.
efficiency, what the general efficiency you can expect from mechanical systems converting mechanical energy into electric energy?
I'm sure I remember talking about it, but I wouldn't be able to tell you anything specific.
Yeah. Anybody? What would be kind of a reasonable efficiency for a system? When can you be happy? When should you be unhappy?
I'm not sure.
So typically, if you get like 70% efficiency, you're doing pretty well with random motion like waves. You probably expect less. But anyhow, we calculated the energy in the cross-sectional area of the pumice, and we learned that the energy efficiency was actually greater than 100%, and there was a reason for it. You remember?
Is it the fixed pitch and roll as well?
That's right, because it also bends this way and it increases it.
Yeah.
So your system right now, as it is, actually cannot bend in all directions. So it really is kind of the fixed surge protect converter right now, unless you get into the third axis somehow, which makes it more complicated.
Just a little bit.
But overall, what efficiency do you think your system has right now, as it sits there?
Probably like less than 10%.
So it makes the LED glow, right?
Yeah. But I mean, as far as like that's just not gonna move well in the waves, I think.
Yeah. I don't think you have 10%. You probably have below 1%.
Yeah, it's terrible.
Yeah.
But the point
So
is
that's
just
right.
to see the principle.
But no. All right. So you want to show us the LED glow now?
It's not in there yet currently.
Huh?
It's not in there currently.
Oh, it's not in there right now.
It's sitting on my desk. But I had to grab one out of the lab. I didn't have one. But the turbine is.
You can see it spin.
Yeah. If you try really hard, the water's kind of foggy.
It spins so fast.
It just spins really fast and stops really abruptly, so it looks like it's not moving, but
Uh-huh.
technically it's blinking.
That's the fittings.
Huh?
The fittings driving you nuts.
Yeah. Where's the leak coming from? Is it coming from the?
Just the end cap. It's coming out of the end cap.
Well, internally. Is it coming from the cylinders?
It's the quick connects.
The quick connects, or really?
Yeah.
Oh, it's still the wrong pipe. Yeah. So you think your cylinders are watertight?
Yeah, they are.
Oh, that's good.
Mostly.
Mostly.
I did have to do. I did.
Water poured out of it. So.
I know.
Yeah.
I want to electrocute anyone.
Did you need somebody to hold it? Let me get this. Put this here. Get down. All right, go.
You can't really see.
You probably could see it better if you hold the base.
I'll be holding the we're wiggling the wrong part.
So just look in there.
Tucker, do you want me to hold the camera?
With the minimal amount of water inside.
Yeah, it's making all kinds of bubbles there.
Yeah, it's because there's a lot.
Cool. All right.
But it works technically.
Yep,
I just have to fix the leaks.
I remember complaining about microgenetics, and you said, I got the master.
Get the good ones.
No, the ones that I got are not it's not those that are leaking. It's the check valves, and then